Hello, my name is Dotsikas and I am currently master student at the University of Patras. I will present you today a work that has been done at Department of Physics, Theoretical Astrophysics Group in cooperation with Georgios Kambilis under the supervision of Kostas Gourgouliatos. This work is related with force-free and twisted magnetospheres of relativistic and non-relativistic magnetospheres. The hypothesis of the complete structure of the neutron star's magnetosphere has been an open field of research for over 60 years since the seminal work of Goldrich and Julian 1969. In this work, we present the structure of an axisymmetric force-free magnetosphere of an aligned rotating magnetic dipole in the presence of a high-density charge in accordance with the model of Kondopoulos, Kazanas, and Friend. The ideal distribution of the electric charge along the open magnetic field lines is a condition that is required to obtain continuous and smooth solutions of the Pulsar equation. We can briefly describe the problem by the equation below, where J, B, and D are the electric current density, the magnetic field, and the electric field, respectively. Magnetar magnetospheres are believed to be strongly twisted due to the sharing of the stellar crust by internal magnetic stresses. For a twisted magnetic field, lines tend to inflate in the radial direction. Applying linear and non-linear solutions, we notice that more and more magnetic field lines tend to cross the light cylinder, becoming open, thus reinforcing the issue of large polar caps. Finally, by using the spin-down formula of Kondopoulos and Spitkovsky, we give an approach for the loss of electromagnetic energy of an aligned rotator in force-free condition. In order to approach the neutron star magnetosphere in the non-relativistic regime, we use the Grad-Safanov equation in spherical coordinates. Here, x is a function of the polar angle, psi is a magnetic flux function, and I is the poloidal electric current distribution. If I receives the following expression, where A is a numerical parameter, then applying different values of A, the magnetic field inflates. You can see the results from the pictures below. We have also used the Magnetofrictional Method to find the magnetic field equilibrium. We find that increasing the twist, the magnetic field becomes more radial, as in the previous solution. We also find out that the two approaches lead to qualitatively similar results. At the relativistic regime, we use the Grad-Safanov equation at cylindrical coordinates for an axisymmetric pulsar magnetosphere. Here, A and N are numerical parameters too, and psi0 is the magnetic flux function of the last closed line. If we try a current distribution of the following expression, only for closed magnetic field lines, then we can conclude that for n equal to 1, for example, which means that we have a linear expression for I, when A increases, then more field lines cross the light cylinder and become open. Here you can see how the field lines become open. The line twist is defined as an integral delta phi along the magnetic field line, the surface footprint of which lie at latitudes of θ1 and θ2. Using the spin-down formula of Kondopoulos and Spitkovsky, we give an approach for the loss of electromagnetic energy, as you can see from the diagrams below. Finally, we find that twisting the magnetosphere leads a larger fraction of open field lines. Because of that fact, the spin-down rate of the pulsar will be higher even if the dipole field has the same strength. Our calculation reached a limit twist about 90 degrees, which is consistent with non-relativistic and analytical solutions. Possibly, if more twisted is added, the field will become radial and be prone to reconnection. Thank you very much for your attention.